Hello from Riyadh. Good morning, good afternoon, good evening. My name is Kyounggon Kim. I'm currently serving as the Associate Professor at Head of Department of Cybersecurity and Data Forensics at Naif Arab University for Security Science. First, I would like to extend my gratitude to the University of Montreal and the Human-Centric Cybersecurity Partnership for hosting the Security Revolution 25 Global Cybersecurity event. It's very honored to participate as the co-host for this important event. These sessions consist of 6 presentations on AI, cybersecurity, and detection of emerging technologies. To begin, I would like to introduce Meshari and Ibrahim, who will present on the topic Deepfake video detection using optimized GenConViT model. Please welcome them and enjoy the presentation. Floor is yours. Thank you.
Yes, hello everyone. My name is Ibrahim. I am with my colleague Meshari and the video detection using optimized GenConViT model. However, we have our agenda here. Yes, I think I am showing the correct one. Yeah. So our presentation have like a logical progression, like any research project. We have the context, problem, they call it introduction and literature review, and methodology, and implementation and evaluation, and discussion and conclusion. But for the time being, let's start into the introduction. And yeah, what are the deepfakes? We have the main projects about deepfakes are AI generated media that has manipulation for audio or for video, and achieving high realism. It is like the VTubers, any AI generated media or voice, like that. So we have a threat landscape in cybersecurity for this one. What is the threat landscape? We have the malicious applications that include disinformation for political lies and financial scams, character assassination, and crucially, the fabrication of false evidence, targeting legal systems and law enforcement. The impact is at its core risk highlighted to national security, is manipulating the political discourse, inciting the unrest and public safety, scams, harassment, and the trustworthiness of digital evidence. The integrity of digital evidence cannot be determined, potentially leading to wrongful legal action or undermining investigations. So what is the problem urgency for this project or for the deepfakes? The current social media platform detection capabilities are limited, and legal regulation are still evolving. That gap is needing advanced forensic tool, and our project is aiming directly to address this by developing a deepfake detection model optimized for high accuracy, high detection rate, and speed near real time, and processing for practical use. And generalizability. It is robustness across different datasets. AI topic across different datasets, manipulating techniques. Okay. We talked much in this slide, right? It is introduction. Okay, what is the problem statement? The problem statement have, like we said, existing methods face 3 critical challenges. Number 1 is insufficient feature extraction. Number 2 is poor generalization to new deepfakes. And number 3 is high computational demand preventing real-time application. Okay. for the objectives. This research focuses on enhancing the deepfake detection by optimizing GenConViT model through three core objectives. Number one, improving feature extraction to extract a significant feature from deepfake dataset, enhancing the model ability to distinguish real fake from another, and also constructing an accurate model and optimizing model for better performance. And we have two complementary datasets that were used. One is Deepfake Detection Challenge from Meta. It is for large-scale diverse training reflecting real-world variation. And number two, Celeb version 2, high-quality and same benchmark for evaluating cross datasets generalization. And we have the database processing overview. Here, the pipeline of the multi-step reprocessing. We extract high-quality face images from using Blaze Face that has the landmarks of the faces, and apply data augmentation to improve robustness. This is a video just for showing our pipeline, how it works. And we'll get to the methodology after that. Good. So the data augmentation has 5 stages. As we can see, the phases of the training, we do data augmentation. On the validation, we don't do that data augmentation, like you see. So yeah. This is our proposed model.
Yes, I think it's my turn, Ibrahim. Thank you very much for what you did. Let's talk about the deepfake and examination method. We tried to examination a lot of models in deepfake, and to find the robust one and the high accurate one. So we tried to do something with CNN, and all of us we know. Hello, what is the CNN and RNN and many of confusion matrix here? Optimize or GenConViT, it's a model get us some promised result. Because what? Because we have here, or we redesigned the GenConViT with the 3 powerful parts, like what we see here in the architecture there. ConNets for special features in the blue boxes, and we have Swin transformer here for temporal features. So we have to analyze the video through 3 powerful parts. One of them, it's CNN, but it's an advanced CNN. It's called ConNets and Swin transformer for temporal features. The other things, or the third part here, we have 2 generative branches, Äì and VAE, auto encoders. These things, or this combine of layers, it has some robust model. It can detect the deepfake videos by just combine all this part together, and with pre-processing, with good pre-processing hyperparameters, we get this result. Actually, if you can move, Ibrahim, to the next slide, please. We have here our optimized model here. We have some features. Why we optimize the original GenConViT? Actually, we need to know if we are remove one of this branch, what's happened. We figure out the result is gone down directly. Early or late fusion, all of us know the early fusion or late fusion is very critical point in any model working in AI or in deep learning. Dual activation, we have here dual activation, ReLo and GLO, and each one we put it in the good or the right place. Attention and pruning. Actually, attention channel, we use the attention channel after our early fusion to just make the model focus in the exactly some details we needed to extract from the videos. As we know, the videos is going to many of the frames. So each frames has some features, some information, some data of the face, and we crop the face. Then the faces is goes to our model. Then we do our or we did our processing. Then we get the result in the end. The result here, it's not like how is it real or fake. The result here is many of numbers. This number is going to sigmoid function. The sigmoid function, he has the predict what is it the video as well. So Ibrahim, can you move to training setup here? For the data we split it. Actually, 70% for the training, 15% for testing, 15% actually for the validation. DFDC, it's the main data set here, but the SECREV data set, it's like a validation for our model. So in each data set we have, or we got some numbers as a result. Hardware, you know, all of us, the GPU is as a limitation here. So we use Lambda A100 GPU. It's online resources. Hyperparameter, yes, we use optimizer functions, and we use loss function in many position in this model. Finally, we use something is called FP16. There is two kind of FP or frame per second. Actually, we have 16 or 32. So we use 16 for just to keep our resources under control. Frame. A metric, we use accuracy and F1 and AUC to just like a measurement for our model. Statistical test here, we have used t-test just to compare our model with another models to see how is it doing there. GradCam, it's something like a good tool to just check where is the model focus on the frame as well, in the face or in the background or somewhere there. So GradCam, it's gets me some directly noted about where is the model focus on this frame. Then the test, actually, the result of our testing and examination, actually, like what you see in this slide, we achieve 96% in DFDC as accuracies, and 95 on SECREV also accuracy. F1 and DFDC, it's 96, 95 in SECREV, 99 as AUC, and 99 as well with SECREV AUC. So in each model, there is a different model here, but you can focus on the right one because this is the proposed model. And the original GenConViT, you can see the result here. The key mark here, you can see the interface speed, millisecond by frames. So you can see in the proposed model is 35 millisecond for each frame. So it's very fast. It's faster than the other models. It's Ibrahim. So like what we say before about the key design, we just combine the EE and VE with the good activation function in good position. So we can say here that the key mark or the black box of our model is how you can put these functions in good or in right positions. And you have to actually focus on the pre-processing stage. The pre-processing is very, very important to get high result. The benefits, it's just we just figure out, because we are a student in the end, and the universities has a lot of support, and Dr. Kim and the others faculty. So we just figure out, we just need to know if we make this or do this, how is this is affected in the accuracy. So this is our real benefits in this. FP16, as what I said before, and Moderator for that, we use some of branches. For example, we delete one branch or one part of this model, and we check the result, and we back add it, and we check the results. It's get us some testing table on that models. Yes, Brian. This is our chart here. You can see the box plot. How is it? All the plot is focused on the center. That's mean the accuracy or the accurate for this model is very يعني it's good to move on. And this is the optimized our proposed model and the loss and accuracy chart. Yes, and here we have something to talking about the video quality. You can see here with the low quality, or which we can see compression file or videos, the result is going down because you have to we have to train the video or train the model more about the high or the low quality videos. So it's like relation between the video's quality and the result in the end. Yes, another chart about the here we have ROC and AUC chart. You can see here the red one is our yes, our proposed model. It's higher. Yeah, this is a GradCam, what I'm talking or talked about. You can see the baseline A3D. Its model is called i3D with attention layer. You can see here there is no any attention in this image. I'm talking about the image in the left of the slides. There is some noise in the background and somewhere, so the model can focus on some part or manipulation part. The original one in the center, you can see there is some noises in the frame as well. And the left one, this is our optimized GenConViT model. You can see the model, it's focused in the face, the position of the manipulation part. Yes, Ibrahim. Here we have model training and prediction. You can see here from this short video how is the how our models work as well. You can see here how the videos in the lady in the screen. This we get this videos from the data set. Actually, the model is focused on the faces directly because there is baseline and open CV. It's like a library. Focus on the faces or crop the faces, then it's going to extract the feature, then he make the predict function. Our contribution here actually about the channel attention layer. Yes, we add the channel attention layer as a one of our contributed here. Early fusion because the original one they focus on late pages, so we just reconstruct the model again, and we get high accuracies in this. And deployment, actually, we create or we the universities help us to build API for this model. Yes, Ibrahim.
Yes, this is the API. You have it to do real-time detection, of course. So when we say real-time detection, we say give it the folder and the number of frames and the generated weights, pre-trained weights, and it will predict and will detect which segment has the fake.
We have only 1 minute or 2 minutes.
Yes.
So we have to be.
This is the key 5 things here. We have for achieved for the architecture and the branches, and we have the attention model optimization and the loss stability. This is the ethical. We have use case, but it is the time is shortage. This is the legislation gap, like we said in the introduction. Our future work here, we need to have expand with new models lighter models like TinyVIT, expanding capability to audio-visual multimodal, and optimizing the pipeline also. This is our conclusion. And if there is any question, please let us know in the comments below.
Okay, thank you, Ibrahim and Meshari, for the presentation. It's amazing. So now let's hear from Abdelwahid. The title is the cyber detection in Internet of Things using the realistic testbed and machine learning. This topic. Thank you, Ibrahim, Meshari again, amazing your presentation, and close the session and please open the presentation, the Abdelwahid. The floor is yours.
Okay. Presentation projects. Okay. Hello, everyone.
Okay. Yeah. Great.
You see my presentation?
Yes.
Could you see my presentation?
Yes, we can see the presentation. Please maximize the size of the presentation.
Okay. Okay.
Yes.
You see it? Great. You see it right now? It's the maximum size. It's full screen.
In the screen is still the PowerPoint slide.
Let's wait. Presentation in Teams. Let's share again. Entire screen. Okay. Share. Now?
Yes, now we can clear. You can see the very full screen. Please give the times within 20 minutes. Thank you. Proceed yours. Thank you.
Okay. Thank you, Dr. Kim. So hello, everyone. Thank you for attending this conference and this presentation. So my presentation today is about my graduation project entitled the Cyber Attack Detection Testbed in Smart Cities. It's a testbed that we have created in our lab, in which we have tried to collect a new data set of attacks that targeted the smart cities. So the plan of this presentation is as follows. We'll start with an introduction of the context of this project. Then we will present the problem statement and methodology. We'll present our contribution a little in details, and then discussion and recommendation before the conclusion. So the Internet of Things is the backbone of smart cities. If we want to give a definition of this term is referred to network of physical devices such as sensors, applications, appliance, vehicles, machines, smartwatch, smartphone, smart TV, etc. So these devices are connected to the internet. They collect and exchange data. This help to make decision. They have been used in different smart environments such as smart farms, smart homes, smart transport, etc. So it represents the backbone of smart cities, and their interconnectivity make them prefer the target of cyber attacks because of their vulnerabilities. For example, an attacker could start by a vulnerable device and get access to more critical systems. For example, if in your home, for example, you have secured everything, but for example, your smart watch or your smart phone is not secured, maybe the attacker will start by this weak point to get access to the critical system. For example, there is some cyber attacks that has been happened before against this IoT device, such as Mirai malware, in which the attackers infect cameras with default credential addresses switches, and then they have used these devices to make or to do DDoS attack. This in this incidents, the big company has been affected, such as Twitter, X, actually, Netflix, Amazon, etc. Also, Ring camera hack in 2019. There's also attackers get access to the cameras in schools and homes. They could talk with the kids. They could represent a violation of privacy and could cause some psychological harms. Also, Atlanta ransom attack in 2018, that the attackers could get the access to video surveillance, which imply that they could delete evidence that has been collected for any days of recordings. This is an example of an attack in which, for example, a ring camera, it's a ring camera attack in which the attacker could talk with the girl, which show how dangerous is the attack against these devices. So as we say, the connectivity of these devices make them a prime target for cyber criminals, and introduce also new challenges for digital forensics. So we have that's make pressing to find the new solutions to try to detect and prevent these cyber attacks. So for that, we have chose this topic for our research. So the methodology of this research, we have started with the analysis of data sets. Then based on this, the analysis of these data sets and the papers, we have decided to create our IoT testbed environment. Then we have performed some cyber attacks in this environment. Then we have collect the logs and generate data set, and then use this data set for deep learning models and machine learning models. So there is some data set that has been collected before, such as MQTT data set, bot IoT data set, federated ton IoT data set. Those data sets have different sensors, different actuators. Some of them they have only sensors, some of them they have only actuators, some they have only they don't have industrial devices. Some of them uses only some limited protocols or some virtual environment. And our analysis also of the research that has been done on this data set, we found that always those research get high accuracy. For example, every time we find research, we found that this research get, by just machine learning models, they got 99% of accuracy, 90 more than 99% of the accuracy. So we have a question why all these models could got this very high accuracy. Maybe the attacks are not more sophisticated. Maybe there is some correlation in these data sets. So, and we don't have prior knowledge to criticize the content of these data sets. Also, we have tested some of them, like Ton IoT. We have got using the random forest 99.89% of the accuracy, and the entry dataset also 99.97 in accuracy. So we have decided to create our environment to try to perform some sophisticated attack, and then collect this dataset and then use it for our research and open it for academic research, and also use this environment for future research. So the objective of our project is to provide a realistic and integrated IoT smart city environment to support research. Also generate a new data set, our proper data set in this environment. Try to use some AI models for intrusion detection, and also use this environment for future research in our university. So this is a picture of our environment in which we have implemented some. We have tried to implement the layers of IoT environment, which are edge, in which there is sensors, actuators, and prep and embedded systems, and real-time data pre-processing. There is a fog layers in which represent, like, for example, network, also like local applications that are used in, for example, in corporate, and the cloud, in which we could use services such as storage or applications. So this is the architecture. This is the architecture in which we have the edge computing. Also, we could divide this edge computing into, for example, we could use perception and edge computing, but we chose the sample architecture. Then we have Testbed in the fog computer, so all the data are stored in Testbed and showed in the dashboard. And also we have computer that use it for camera streaming. Then the different information also stored in cloud. We have just simulate the cloud using our local server. So in which we have used the Testbed was for detection and a backup server, in which we store our logs. I will explain that further. So this is in the perception layer. We have smart farm, which has different sensors, and we have temperature serial sensors which is connected using USB, and we have a camera. So let's just go and explain each of them. So smart farm is a smart farm ASP30T key studio microcontroller. They have in this farm there are different sensors like temperature, humidity, steam, light movement, water level, etc. They have also actuators which use it to take actions in this smart farm. So some of the dataset that we have mentioned before, they don't use actuators, just use sensors. So for example, actuators for enabling pump, fan, open the door, etc. So to connect this smart farm to our edge computing, we have used an Arduino program. So we have developed an Arduino program, and then we have implemented this. We have installed this program in the smart farm in its microcontroller. This Arduino program enable automatic and periodic read and send of the value from sensors to our edge computing, and also it enable receiving comments from the edge computing. For example, comments for opening the door, for running the fan, etc. So they have used for the exchange with the edge computing. We have used the MQTT and HTTP protocols. So this is an example of the code of Arduino, in which we, for example, read humidity, temperature, and different value, and send them, then publish them in this topic in the edge computing. So the second component is serial temperature sensors, which is connected using USB to our edge computing. And this sensor has a built-in program that periodically read and send the value to the edge computing. The third component of this perception layer is the camera. So to connect this camera to our environment, we have used the mobile application of Tapo C200 camera. Then we have configured the network of this camera to be connected to this environment. Then we have performed the streaming of this camera in this computer. And in order to collect the traffic of this camera, we have used the gateway. So every communication with this camera is recorded in this gateway. Okay. So for the edge computing, in which we have mini computers, these computers, in this computer we have installed Ubuntu 24, and these mini computers have two interface, so wire and wireless interface, and also they have limited storage space. They have only, I think, 23 gigabyte of space that we including the space used by the system. Then we have installed Node-RED, is a visual tool for creating flows and enabling, for example, automatic processing and simulation of communication with sensors and also emulation. So we have installed network in this Node-RED in this mini computers, and also we have installed in the edge computer. So this is the flow of Node-RED for the smart farm. For example, here we have listener for that they have subscribed to broker for different topics, and then they receive data and process the data using these functions, and then send the data to fog computers. In the smart factory is a simulation of smart factory using Node-RED, in which we have also Modbus and different protocols such as HTTP to send the data, MQTT. This is for the serial temperature. It's connected to serial port, then receive the data, process it, and send it to thanks board in the fog computer. So this is the same thing. This is the MQTT subscriber, and this is the pre-processing in which we have used the JavaScript and Python code. For example, if we receive data and we want just to transform it before send it to the edge to the fog computing, that reduce the amount of data, the size of data that we should send, and that perform some real-time processing of the data. And this is the publisher which send the data to the fog computing. So for the smart farm, we have sensors which receive the data and then process it and send it to the edge computing. And we have actuators. We have also configured actuators. For example, if you press these buttons, different action will be performed in the smart farm. So to monitor the traffic in our environment, we have used different tools. We have used Wazoo, which is the same solution to collect logs about different activities that happened in these computers. We have used Suricata, is an open source tools, an IDS, and also could configure it to be like IPS to detect some cyber attacks that has been happened in our environment. And the most important tool is Zeek, which we have used. You have configured these tools in order to collect every traffic that happens in our environment, and this traffic will be converted to a data set. So why we have used Wazoo and Suricata in our environment? I see to detect that some cyber attacks has been happened as expected. So to be sure that that's only, for example, some sample attack like DDoS, password, brute force, etc., has been happened as expected. So if we perform then some sophisticated cyber attacks, we will be sure that also these attacks work as expected. So to configure was we have used group configuration from the server. So we configure a different machine, just putting some rules in the server and then send them to different machine. For Suricata, we have download some well-known rules like the DOS spoofing, brute force rules. For Zeek, as I mentioned before, I said that in each of these computers, we have a problem of limited storage. So we have developed a Python code that sends periodically the logs collected every 12 hours to the backup server, and delete this log from the local machines. So it collect normal and suspicious traffic. This is the code of it's an example of the code of the Zeek that collect the logs and send them to the backup server. This is the structure of the logs in the backup server. For example, if we say here, each of these computers have IP address. So we have created folders of these computers in the server, and in each of these folders we have the date and the hour of the backup, and each of these folder we have different logs that has been collected. So after the installation of and configuration of the edge computer, we have configured the edge computer layer. We have configured the fog layer, in which we have created we have used the thanks board, and we have created gadget component for each of the sensors. For example, this is temperature, humidity, soil, human detection, movement, rain detection, etc. This is from the smart farm. For example, here we have temperature, bar of temperatures from the serial temperature sensors, and we have simulations at machine vibration, pressure, etc. from the factory, simulation factory. So for the cloud, we have not used paid cloud. We have just simulated the cloud by our servers. We have used the Promox environment. And in the cloud, we have installed backup server to collect the logs. We have installed another version of the thanks board, and we have installed the SIM solution Wazoo. For example, we say that during the attacks, we detected high activity detected. So that's confirmed to us that the attack has been done as expected. This is the environment that we have used. Promox is a virtual environment for virtualization. So in this environment, we have installed different server for the cloud. Then after the configuration of the fog, edge, and cloud layers, we have started to perform some cyber attacks using some Python scripts from Kali. So we have used Kali to perform these attacks. This is an example of the logs collected during the HTTP flooding attack. So we have performed some different attacks: DDoS attacks, spoofing, sniffing, man in the middle, MQTT flooding attack, DNS, unauthorized access, brute force, login, port scanning, etc. So this first part is the main objective of our project. So when we have created our environment and we have performed attacks, we have collected the logs, and we have created our dataset. This is our first and the main contribution. Then we have tried, because we are not yet finished all the attacks that we have expected. We should also perform some more sophisticated attack. So we have just tried to generate this dataset and try to perform some machine learning model to be sure that our work is as expected, and then we will try to perform some more sophisticated attack. So for the part of the
finish the 1 minute, please.
Yeah.
Please finish in 1 minute. Yes, please.
I just take 13 minutes right now.
Okay, good.
I think I have 7 minutes also.
Okay.
I have 7 minutes to finish 20 minutes.
Fine.
You have to say 20 minutes.
Okay, great.
Okay, I will try to finish because I put a chronometer in front of me to see how. Okay, I will go fast. Okay, so after that we have generated our data set. We have collected 10 gigabyte of the logs. We have converted this to dataset to CSV dataset. So these are some statistics about the normal and the attacks packets collected and for different attacks. So this is different field that we have collected in our data set. So in our logs, and that we have put in our data set. So after that, we have performed some pre-processing methods to clean up some corrupted data or missing data, try to select relevant features, remove some irrelevant features, some such as, for example, IP address, etc. So we have removed these fields, and we have just keep some of them. This is the dataset before and after balancing. So this is we say that the normal traffic is bigger than attack. It's normal because this is collected for during all the day, and this is collected during the attack. Some attacks also give more traffic than others. It's normal. This okay. We have tried to balance. And then we have tried to apply some machine learning models such as logistic regression that we're known for binary classification, and we have used also random forest. So those are the accuracy for logistic for detection of the attack or not attack. So for random forest, we have achieved 97%. We have tried to apply these models for different for attack detection. We have not get to high accuracy. We have got all, for example, only 87% and 72% for the logistic regression. This is for random forest. Okay. And also we see that, for example, here for botnet, we have precision and the recall, and this value are reduced. Why? Because the relationship, because in the attacks, there is a relationship between packets. So we have decided to use them as sequences. So we use 10 by 10 packet to based on them to detect if there's attack or not attack. So we have used LSTM model. So based on this model, we have chosen a part. We have achieved this accuracy. It's 93%. It has considerably improved. And also we see here, for example, for botnet that it has been increased, and for other. So for our model, we have good accuracy for random forest, and also for others for the attack detection. We have needed to use sequence models that process sequential data or timing data. So as a recommendation or as future work, we will add some new devices in our environments, and we will try to perform some more sophisticated attack, and we will test some more machine learning models, and we try to collaborate with our with different faculty in order to use this environment for other researchers, like for cyber attacks and also for digital forensics. This is example of our environment. I will not show it all, just I will. This is the smart farm. Okay, this is the smart farm. This is the edge computing, different camera. This is the node read, for example. This is the actuators. This is the sensors reading. There is also some other devices that we are not yet included, integrated in our environment. This is the edge computing. This is other sensors that we have not yet included. This is actuators working. This is other sensors that could integrate in this environment. So this is the reference, and thank you very much.
Okay, thank you. Great job, Abdelwahid. Amazing presentation. Okay, excellent. So now we are moving forward to, we have another exciting presentation by Elham and Nada. Yes, plus yours. Please to prepare to your presentation. Yes, plus yours, Elham, Nada.
Good morning, everyone. My name is Elham Felemban. Today, I'm honored to present our graduation project titled Improve Dark Web Monitoring with Advanced Crawler and Machine Learning. Our project overview: the project aims to develop a dark web crawler that uses machine learning to detect and classify illegal content in support of digital forensic investigation. It can access hidden onion sites, bypass CAPTCHA barriers, and identify threats like cybercrime or terrorism. The crawler works on both dark web and surface web using hyper machine learning, SVC, and random forest for classification. Our motivation is to address the growing use of dark web for illegal activity and provide law enforcement and researchers with tools for real-time automated threat monitoring. Contribution: This research aims to develop an advanced dark web crawling, naming Äì The machine learning that overcome the dark web challenge, develop advanced technique to bypass CAPTCHA, apply a hybrid classification system using machine learning, random forest, and SVC for automated detection and classification of illegal content. This diagram shows the complete methodology of our system, from crawling to classification. We begin with the crawler, which has a built-in adaptive CAPTCHA solving mechanism and support multi-mode crawling. This allows to access and navigate dark web pages, even those protected by CAPTCHA. Once access is approved, the data collection module captures text, image, and URL from hidden server and generate a private dataset and merge with public dataset. We clean and pre-process the data, then train the Hyper SVC and reinforce for classification. Finally, the model classifies content in real time with as either special or benign, enable accurate and scalable dark web monitoring.
Our crawler has the following key features: multi-crawling, training or prediction, captcha processing, manual or automatic, data extraction and analysis, and various output formats. But the two most important elements that represent our contribution are multi-crawling type and multi-captcha handling method. For crawling type, we have two types of list: training list and production list. The training list is used for dataset collection because the class and type of the links to be crawled are determined previously, and the crawler classify and determine the type based on this list. But the production list is the list that will be used to classify the site content using a function based initially on keywords but later replaced by the machine learning models we have developed. This list will be used when the crawler is used in a production environment. For captcha handling, we have two modes, manual and automatic. Manual mode is used for complex captchas that won't be solved automatically. So when the crawler finds the captcha, it opens the browser and waits for the user to solve it. But for automatic mode, the captcha will be solved automatically using different manners, including OCR based on deep learning, APIs, and Python methods. This is an example of manual handling where the crawler will wait for the user to solve the captcha. For automatic captcha handling, OCR or Death by Captcha API, CapSolver API, or numeric sum function will be used. To get around the captcha, we tried to create a deep learning model. This model is OCR model. To train this model, we used a well-known Kaggle dataset called the captcha dataset, which contains more than 113,000 images. Then we have used a deep learning model combining CNN for feature extracting and bidirectional LSTM for sequence modeling, which is specialized in text processing, ending in a softmax layer with CTC loss. This model reached its best performance in the 9th epoch. We then integrated this model into our crawler to extract the text from images to solve the captcha. If our OCR is failing to resolve the captcha, we use an online services that use deep learning models. These APIs are Death by Captcha and CapSolver. This is our crawling system architecture. It starts with the user input file and then take the user options in 5 things: crawling mode, is it automatic or manual, deep of crawling, and if the user wants to using ClearNet or dark web, the list type, is it training or production, and the captcha attempts. After that, the crawler loads the list URLs provided by the user. Then it ensures secure and anonymous connection via the Tor network before proceeding. Each URL is attempted up to 3 times to handle unstable onion service. If it succeeds, then it will check for captcha. If it's failed, it will store the link in file named loadfail.txt. If captcha is detected, the system attempts solving it either manually by prompting the user or automatically using tools like OCR, Death by Captcha, CapSolver, or reCAPTCHA solvers. If the captcha cannot be solved, the system logs the issue and moves to the next URL. When the captcha is bypassed, the crawler grabs session cookies and extracts content such as HTML, text, links, and images. Then, for the content analysis, the extracted data is analyzed for keywords. The label determined based on the list type chosen by the user. If it's training or production, the label will be based on pre-classified list or count keywords. After that, the result it will be saved in formats like JSON, reports, and screenshots for forensic or analytical use. Then, if the current depth is below the maximum, subpage links are explored recursively. As last step, the crawler checks for more URLs. If none remain, it saves final output as JSON, and others then exit with summary statistics.
Now we will show you the result on visualization. Crawling result. As shown in the screenshot, each crawling domain or onion URL is stored in its own folder, and these folders are automatically named using hash or unique identifier of the URL. Inside each folder, the crawling saves all the collected content, including main page and sub-pages. It will be able to access. These sub-pages are stored in structured files such as JSON or text containing extract text, metadata, and links. The pie chart provides a clear visualization of crawling result, breaking down the outcome of all URL processed by the system. The green segment shows 53.5% of the URL were successfully crawled. The yellow segment represents 26.2% show the failed crawler, typically used by timeout issue. Finally, the purple segment at 20.3% shows invalid URL, which could be no longer active on dark web. Generating text dataset. This shows a snapshot of generated text dataset after processing the crawling content. Machine learning result. This presents the performance evaluation of SVC model used for classified dark web. On the left, the confusion matrix shows how well the model performed. It correctly predicted 243 suspicious cases and 85 benign. There were only 5 false negative suspicious cases misclassified as benign and 20 false positive benign pages misclassified as suspicious. On the right, we have classification report. The model achieved an overall accuracy of 93%. The second model was random forest. Related to the performance evaluation of random forest model, here we achieved 96% overall accuracy. With confusion models, we can see in the right, the RF model correctly predict 241 suspicious and 98 benign cases. It only produced 7 false positive and 7 false negative. Limitation and further research. As with any research project, there are areas where improvement and future development are both possible and necessary. On the development side, one of the main goals is to build a centralized threat intelligence platform. This platform will integrate our crawler to perform real-time detection and classify, allowing security team or law enforcement to monitor and respond to emergence threats more effectively. From crawling perspective, crawling more URLs, support data export and integration with external security tools like SIEM or threat intelligence platform, increase the dataset by crawling benign URLs. To conclude this study successfully developed advanced dark web monitoring framework powered by IDMAC machine learning crawler and a hyper machine learning model combination SVC and random forest. The key innovation of our system include automated CAPTCHA solving, smart URL filtering, and high precision classify of both text and image. Thank you.
Thank you for presentation, Elham and Nada. Yes, the darknet investigation is very crucial and very important to the domain. So thank you again for your presentation. Next, let's welcome to the Adel and Abdulrahman to the stage. Their project is the hybrid approach for phishing detection in email. Adel and Abdulrahman, floor is yours.
Hello everyone. It's our presentation is showing or still? Hello.
Yes, please. Yes, please. Start presentation. Yes, go ahead, please.
Okay. Hello everyone. Good morning, Professor, Doctor, and community member, and our colleague. My name is Abdelwahid Subahi, and with my colleague Äì The Cybersecurity, and today we will present our graduation project. Our graduation search about the hybrid phishing, hybrid approach for phishing detection email. And this is presented by, this is supervisor by Dr. Kim, and we are a master student at Naif Arab University for in cybersecurity and digital forensic science. So today we will walk through the objective, methodology, result, and significance of this work. In the beginning, the phishing attack continued to be one of the most whispered cybersecurity challenge. Attacker exploit a human trust and technical vulnerabilities using the deceptive email to steal sensitive information or infect the system. The traditional system filter, security filter are singular detection. The system have struggled to keep pace and increasingly sophisticated phishing attacks. And this has created a critical need for intelligent adapter solution capable of analyzing the multiple features of the email. So our motivation in the first, the phishing threat overview. Over 932 phishing incidents were reported in Q4 in 2024, based on the anti-phishing working group report. The case an estimated 2.9 billion in financial loss in United States alone. So this is existing model. Also, the existing model are limited by single layer analyze and struggle with the real-time detection and false positive. And to addressing this issue, our project proposes to a hybrid framework that analyzing the URL, email body content, and attachment to improve the detection accuracy and reliability. So the most existing detection, as we say, model focus only on just email, one of the email components, such for example, the text content, URL, or attachment for the email. And this limitation approach make the vulnerable of multi-layer attacks, where the attacker use several techniques at the same time with the attack. Additionally, this model often suffer from high false positive rate and make scalability challenge in real-world environment and poor adapter for new attack patterns. So our objective goal was to develop a hybrid phishing detection system that combine the strength of deep learning and role-based analysis. And also we aim to create a model that could accurately analyzing the email text and inspecting the URLs for the email and verify the email attachment. Our key objective, including the enhanced accuracy, reducing false positive, and ensuring the accessibility and making the system scalable for practical deployment. So the methodology overview, our system use a multi-stage layer detection, and we are focusing to analyzing the email body using deep learning, especially Roberta-based BLSTM model with attention mechanism. And also for the URL and attachment, we use a role-based check to ensure the false and to ensure the fast and reliable verification. So we will continue with my colleague Äì The Cybersecurity from the methodology. Thank you very much. Adel?
Adel, your voice is muted. Hello, Adel, your voice. Yes, please turn on your voice, Adel.
Yes, can you hear me?
Yes, good.
Sorry. Okay. So can you see the screen?
Yes, sure. Please go ahead.
Yes, I will introduce this methodology after the explanation of my colleague Abdurrahman, what he said, and how is this project is significant. This methodology is starting by data collection. We use 4 datasets from public source. We use the Enron dataset for non-phishing email, and also we use the Corpus dataset for phishing email. And after that, we combine the dataset for email body together to make it together and make the model train on it. Also, we use the virus share MD5 for checking the attachment and the URL for the sender reputation. This component is very important for decide if the email is phishing or not, and we use it as a hybrid approach to be analyzed multi-component from the email, like the header and URL and the body. The core business here, it's actually about the body analysis, mail body analysis by using Roberta and BI Roberta, which is a pre-trained transformer. And we also add the BILSTM algorithm with the attention mechanism on it. Also, we integrate the rule-based check to check the URL reputation, and the MD5 hash to check the static analyzing for the attachment. Also, at the final, it's classified the email as a legitimate or phishing. The dataset analysis here, if you can see the slide, the legitimate and phishing email, it is balanced between the legitimate and phishing. The legitimate is around 6,500. Also, the phishing email same as the count of the email body, and the URL same thing, but we don't need here to balance because it is a rule check. Also, the MD5 same as the URL, it was a rule checked, and it's taking from the virus share. And we can replace this in as an API if we apply it in the real time to check the everything by the API with added with the body analyzer also. The data pre-processing here, as we said, we use it the Enron and the spam assassin and the fish tank. Also, after that, we clean the dataset and set up it for the training model by label it, and we make it the tokenizer by Roberta. Also, with the BILSTM with the attention mechanism, we split the dataset into 70 and 70 for training, and 15 for testing, and 15 for validation. Also, in the data pre-processing, we label it the body, and before we cleaning the body by parsing the main body content, and we remove the unnecessary data and the special characters. One sample of the mail body, if you can see it here, from the CSV datasets. that it is a text, it is all text, and the model is training on this data set. This figure is showing the most common words using in the phishing email, like money, fund, and account, verify, click here. The model is considered and pay attention to these words, especially to be used in the phishing and decide if it is phishing or not, and also integrated with the URL reputation and analyzing if the attachment, if there is any malicious attachment in the email. Why we choose Roberta, not Barrett? Roberta is an optimized of the Barrett. Barrett is it was initially developed from Google, and Roberta it is improved from the Facebook, but we choose this because it is training on larger data sets, and it is a feature with the dynamic masking. The model selection was we selected by first we choosing the Roberta first to be analyzing the contextual word representation, and it was highly effective for text classification task. After that, we found some gaps in the Roberta. It is not very good in the sequential context processing. We add the BILSTM on it. Also, we add the attention mechanism to pay attention to the important words used in the phishing email. One example of the BILSTM attention weights, if we take this sentence, for example, your account will be locked, click here to verify it now. It will pay attention, it will give a weight value for every word, backward and forward, from left to right and right to left. And if you see the value here, if there is a more than 0.030, it means it will give more attention to the word in the text analyzer. Also, the attention mechanism, it is very good to make attention to the some word and highlight the phishing words and give it a token also. Like if you see account, it take more than 0.01, like 0.02 to every word, and it is collected together when it is collecting, when it is existing in some word more high value, like click and go and verify. So it will consider this as a phishing also. For the result of this model, we test the model on unseen data to prevent it is overfitting or memorize the data that was training on it. We get the confusion matrix was perfect to detect the phishing email and legitimate email. Also, the metrics of the accuracy and precision and the recall was excellent and high accuracy, and that's showing it is a robust performance in the phishing detection. For the future work, we will enhance the model to be work in multiple language for multi-language like Arabic or other language, and also we want to enhance the model to detect the QR code also embedded in the body, and if we apply it in the real time, we can develop the monitoring dashboard that's analyzing and make the administrator analyze the flow of the emails, like email gateway, for example. The conclusion, we design and we develop a hyper detection framework that integrates URL analysis and MD5 checking and verification with the core body analyzing by utilize the Roberta and BILSTM with attention mechanism, and we get very excellent score 96%, and we can implement this in enterprise or any environment that can be in real-time detection for phishing and prevent and predict the user, make the user predict if he facing the phishing or something like that. Thank you, and if you have a question, you are welcome.
Thank you so much, Adel and Abdulrahman. Thank you for the insightful presentation. Now, let's move on to our next speakers. The next two presentations are related to emerging technologies detection and related to drones. It's very interesting topics. Plus yours, Bashar and Sarah. Plus yours. Bashar, Sarah, if you please prepare the presentation, please share your presentation. Yes. Please
Hello.
check the full presentation.
Yes, you can show it.
Yeah, I can see. Oh, good. Excellent. Great.
Okay. Hello, everyone. It's a great pleasure to be here with you today at Cybersecurity Revolution. My name is Meshari Alhearri, a student at Naif Arab University for Security Science, College of Cybercrime and Digital Forensics. I'm honored to present our graduation project under the supervisor, Dr. Kim. Thank you for being here today. Let's begin our presentation. Here we'll be explaining this content, which includes the background, the problem statement, research objectives, literary review, and contribution. And my colleague Sarah she will be continue with methodology, final output results, performance, conversation analysis, limitation, conclusion, and future work. Background overview: drones are now widely used to support public safety and improve real-time response to danger situations. They can quickly reach different areas and capture live video from the sky, which makes them very useful in emergency cases. Therefore, using drones for weapon detection helps improve safety and reduce crime, but detecting weapons in real time is still a challenge. So, in our project, we propose a novel two-stage weapon detection AI system termed TS-YOLO, which utilizes the YOLO deep learning model to improve detection performance in real-time surveillance scenarios. In this slide, we will show the detection result of baseline one-stage model. As we can see in the video, the one-stage model is based on detecting objects from the entire image, which makes it difficult to detect a small or partially hidden weapon because of the long distance and background noise. This leads to lower accuracy and weak performance in real-time application. That's why we decided to improve this by using a two-stage approach. Weapon detection is very important for keeping people safe in public areas, but traditional methods like manual check or basic surveillance cameras are not enough, especially in busy or dynamic places. There are challenges like small weapon or long distance that make detection harder. And when detection is not accurate, it can lead to missing real threats or slow emergency responses. That's why we need a smarter and faster solution. Our project has 5 main objectives. First, we want to develop a weapon detection model that works in real time and gives reliable results. Second, we use a two-stage approach based on YOLO to improve accuracy. Third, we aim to reduce false negatives, especially when it comes to detecting small or partially hidden weapons, which are often missed. Fourth, we make sure the model performs well on both RGB and IR images. And finally, we want the system to process quickly, so it can be used for fast response in real situation. Now I will highlight the key contribution of our work. First, we developed a two-stage weapon detection system called TS-YOLO. This system separates human detection from weapon detection, which improve contextual accuracy, especially when weapons are small or partially hidden. Second, we tested our system using the Naif weapon dataset, which includes real images collected from a first responder drone. This allowed us to evaluate the model in realistic environments. And finally, we performed a detailed comparison between our two-stage model and the traditional one-stage model. In this section, I will present a summary of related studies on weapon detection. We reviewed several recent papers to understand the methods used, their results, and the main gaps they faced. This helped us identify the weakness in existing work and define how our project can improve on them. Most of the reviewed papers used different versions of YOLO for weapon detection, including YOLO version 5, YOLO version 7, and YOLO version 8. Some researchers added extra techniques like attention mechanism or ensemble models to improve accuracy. While the results were good, many studies still had problems such as missing small weapon, low performance and poor lighting, and limited testing in drone-based environments. This gap showed the needs for a more accurate and robust solution, especially one that can detect small weapons in real time using drones, which is the focus on our project. For example, the last paper used attention mechanism to detect a small weapon, but they still had issues under changing lighting. Now I will highlight the key challenge we observed while analyzing previous work. Based on our review, we found some common issues in the existing study. First, most of them used models like YOLO, faster RCNN to improve detection speed and accuracy. However, it's still difficult to balance between real-time speed and high accuracy. Also, many studies used limited and non-diverse datasets, which affects the model's ability to generalize. And finally, many models don't perform well in challenging environments. For example, in low light, crowded scene, or when the weapon is small or hidden. These issues helps us shape our project goals, especially focusing on detecting small weapons and handling different environments. Thank you, and my colleague Sarah will be continuing.
Thank you, Meshari. Hello. I will start with the YOLO architecture. To see the stage, I will first talk about the YOLO architecture, the model powering our system. YOLO stands for You Only Look Once, and its core strength lies in performing object detection in a single forward pass, which allows for extremely fast processing. It consists of three main components. The first one is backbone extracts essential features from the input image. Then NIC aggregates and refines features across different levels. And the head produced the final output, bounding boxes and class probabilities. Because of its unified structure, YOLO is highly optimized for real-time detection tasks. In our project, we used YOLO as the foundation for a customized two-stage detection pipeline designed to improve contextual accuracy, especially for detecting sensitive objects like weapons. The overall system flow chart. This diagram shows the overall of our system. In stage 1, we start by detecting all humans in the video frames using YOLO-based model. This works for both RGB and IR format. Once the people are detected, we move to stage 2 is triggered instead of scanning the whole image again. The model focuses only on the areas where humans were found. This focused search acts like an attention mechanism. It helps the system look closely at just the important part. By doing this, the system becomes faster, more efficient, and more accurate, especially in hard conditions like low light or IR footage. This two-stage design helps reduce the false results and gives more reliable weapon detection. After applying our trained models, this is the system's output in our scenario. It successfully detects both humans and handheld weapons in RGB and IR video frames. Each armed person is marked with a red box, and any detected weapon is highlighted in blue along with its label. The system also displays live counters showing the number of humans and weapons detected in each frame. This provides clear and fast visual feedback, helping a surveillance team quickly identify threats and support real-time decision-making. Here is a side-by-side comparison of the RGB results. On the left, we see the one-stage model, which misses some weapons. On the right, the two-stage model successfully detects both the human and most weapons with clear bounding boxes. This approach gives more reliable insight and makes it easier for security teams to understand the situation. And here, the same comparison using IR frames. Again, the two-stage model detects the weapon more reliably than the one-stage. This added clearly in dark environment helps surveillance operators respond faster and with more confidence, even under poor visibility. This slide shows a comparison between the one-stage and our two-stage model using RGB images. The chart on the left shows how much the detection accuracy improved. For example, the old model reached around 52%, while our model goes above 99%. That means the system is much more accurate in identifying weapons. In the right chart shows the precision or how confident the model is in its predictions. In some classes, like pistol and knife, both models performed well, but for more challenging weapons like guns, our model did much better. This slide for IR shows the comparison between one stage also and two stage. On the left chart, you can see that the overall detection accuracy map at 50 improved clearly with the two-stage model. It reached over 97% compared to about 91% with the one-stage approach. In the right, we see that the precision also increased across all weapon types, especially for guns and knives. This proves that our method is not just accurate in daylight, but also reliable in more difficult conditions. The system performs well, but it has some limitation. It can detect weapons that aren't carried by people, and it depends on human detection first. Also, the two-stage process may use more resources and cause slight delays. And in some RGB cases, precision may slightly drop, but weapon detection, especially for the guns, remains highly accurate overall. These are expected trade-offs and they don't take away from the system's core value, delivering accurate, focused detection in real-world drone surveillance. To summarize, in this project, we developed a two-stage detection system based on YOLO, designed specifically for drone-based surveillance. The system works by detecting humans first and then checking if any weapons are being carried, which helps reduce false positive and improves detection accuracy. In our model showed strong results in both RGB and IR video and performed well even in low light or nighttime conditions. This makes it a practical solution for surveillance tasks that require quick and accurate results, especially in environments that need monitoring around the clock. Now for the future work, first we aim to try to detect weapons even when no human is present in the scene. Second, we want to save resources by focusing on suspicious individuals before analyzing for weapons. Third, we plan to make the system run on low power devices. And finally, we plan to explore transformed based models to make the system faster and more accurate. These are the main sources that support our research and helped us design and evaluate our system. Thank you for your attention.
Thank you, Meshari and Sarah. That was a very impressive session. And now, let's welcome to the last speaker of this session. The title is the drone detection using CNN YOLO elements and red fusion with attention for security. The speakers are Sanat and Shafi. The floor is yours. Sanat and Shafi.
Hello, Dr. Kim.
Hello.
Yes, the presentation will begin by Shafi'i, and then I will continue.
Okay, great. Okay.
Hello everyone. Good morning. Hello, Dr. Kim. I'm happy to be here today. Can you hear me?
Yes, we can hear you very well.
And
Go
I
ahead,
hope
please.
you can see my screen.
Yes, perfect.
Okay, thank you, Dr. Kim. We appreciate this opportunity to present our project today. My colleague and I will be presenting drone detection using CNN, YOLO 11S, and late fusion with attention. This project was supervised by the Professor Chona Kim, and we thank our Department of Cybersecurity and Digital Forensics. We will continue from here. Our agenda today will be introduction, literature review, research methodology, implementations, analysis and discussion, and finally conclusion and future work. In our introduction, drones, as we know it, have a lot of benefits for human beings, and every year they develop new technologies for drones. They are used for crowd monitoring, delivery services, security and surveillance, but they also pose a lot of threats lately. If you can visit defendsolutions.com, you can see the latest drone incident is that like smuggling, hacking, also unlawful surveillance. If you can check that website, you can find all the latest events which have been used by drones. The latest event I could see was maybe May 5th, 2025, which is like 4 days ago. So also not only drones can be used for like physically, they can be used in cyber ways, such as hacking, using network, using wireless data interceptions, malware delivery systems, reconnaissance, and targeted home-based attacks. So we propose a model that can detect drones from using video and audio of the drone. The background of drone detection goes back to radar detection, radio frequency detection, acoustic-based detection, and also visual-based detection, which all have their own limitations. And in our project, we focused on the acoustic and visual side of the of drone detection. Individually, these methods have limitations. For example, acoustic-based detection can have issues if there is a background environmental noise and you cannot hear the drone sound. Also, visual-based detection have background clusters, decreased visual, or if the drone is flying behind a building or a tree, it has issues. Our objective of this project is to address the available data sets, because when we were doing our literature review, all the researchers had problem with data sets. Some of them used synthetic data sets, some of them use limited data sets. Also, we intend to improve detection accuracy and robustness by mitigating weaknesses of the individual detection methods, or develop a late fusion model that can combine both methods, audio and visual, and after that evaluate our proposed model to the existing late fusion models or fusion models. The significance of our project is to overcome limitations of individual detection methods, introduce a lightweight late fusion AI model that can detect the drone in real time, enhance cyber physical security by countering unauthorized drones, support anti-drone measures in cybersecurity, detect and classify drones. In scope, our project, we focused on 3 specific drones, DJI M30T, and Hancom 550. Our contribution to this project is that we created our own data set, custom data set, collecting all our data from these 3 drones. We evaluated acoustic drone detection models. We evaluate visual drone detection models, and we also develop and evaluate our own late fusion model that combines both modalities to see if we improve the accuracy of the drone detection. In literature review, we focused between the year 2020 and 2025. We collected over 25 studies for our literature review, between drone detection acoustic-based, drone detection visual-based, and drone detection fusion-based. Here are 3 examples of our literature review. The first one is based on acoustic drone detection. It was published in 2021. The second one is visual, and the third one is fusion. The problem statement is that the individual drone detection models have a lot of issues individually, but we intend to combine these models to complement each other and to increase the detection. Our methodology is that we collect the data set, our data set visual and acoustic, then extract the features, train model, AI models, get predictions from individual models, and then combine the last results in one fusion model, and then that fusion model will give us the final prediction in real time. In our data collection, we collected drone data set, acoustic and visual. We collected the drone audio from outdoor and indoor drones, except for Hancom, which was a little bit hard to collect data indoor because it's big and we couldn't fly it in the lab. Our data set, we also acquired a data set, environmental background noise data set, so we can make our model, our data set balanced and to make the audio model robust and able to detect the drone sound under any condition. Also, we collect, as you can see, this is our audio data set. First, we collected the audio in raw audio signal, and then we extracted the male spectrogram features for the acoustic model training. And as you can see, this chart, it shows how the dataset distribution was handled, 25% in each class, including the 3 drone types and environmental non-drone sound. And also we collected visual data, video, 15-minute video of each drone. And also we acquired a bird dataset, publicly available bird dataset, to make the model to distinguish between the bird and the drone. As you can see, the figure is on the right. And we extracted 4 frames per second using OpenCV, which made our dataset about 12,000 frames of all our visual dataset. And we also did our manual annotation or labeling using a Make Sense open source tool, and we extracted in YOLO format. So you can see here, this the first is the frame extraction and labeling, and this is the distribution. As you can see, our bird dataset was a little bit smaller than the drone data, the data we collected ourselves, and we couldn't find a bigger bird dataset. As you can see here, we used a CNN model for acoustic drone detection, and our CNN model takes mile spectrogram features as input, and it has two convolutional neural network layers and 2 max Boolean layers to minimize the computational usage of the model. After that, 1 fully connected layer that collects all the output from the convolutional neural network layers, and final prediction of output. Also, we used a CRNN model to compare between our acoustic CNN model and the CRNN model. The CRNN model was a little bit complex and huge, and it struggled a little bit with real-time drone detection when we trained and tried detection. Our CNN model outperformed the hybrid CRNN. Thank you everyone for listening. From here, my colleague Sanad will be continuing.
Hello everyone. Hello, Dr. Kim.
Yes, go ahead, please.
Yes, my sound is good. Okay,
Yes, great.
now I will continue from the visual module. The visual module, we use 2 modules, YOLO 11, YOLO 8S and YOLO 11S. And for YOLO 11S, we choose to use with our Fusion approach because the YOLO 11S consists of 181 layers and with 9.4 million parameters with 22.6 G-flops. That means is a deep architecture and lighter than YOLO 8. We not include explanation of other modules because due to the short time for presentation. The architecture of YOLO 11 consists of 3 main parts. The first part is backbone for feature extraction and and head. The backbone is the YOLO 11S have enhanced backbone rather comparing with other previous YOLO version, which include attention mechanism for enhanced future learning, which is with spatial primed future fusion block for spatial information aggregation, and with NIC use future primed network and path aggregation network with better upsampling and future fusion. That means it's better for classification. And with head, it's use onshore free mask head to detect objects without relying on the predefined onshores. The YOLO 11S provide us a higher detection accuracy, especially for on drone, is lighter and faster than YOLO 8S, and better performance in cluttered complex scenes. Spatial attention improves focus on small, partly visible drones. Now we will talk about our fusion module, late fusion attention module. Our late fusion attention module is combining the audio CNN and visual YOLO 11 outputs, and have attention-based weighting using confidence scores and drone distance. Is lightweight and efficient to be suitable for real-time drone detection. The total parameter is just only 72.868 thousand parameter. That means lightweight and real-time capable. As we see in the architecture here, the two output of acoustic and visual. Then the first layers, we have a projection layers to project the audio and visual feature to share the 128 dimensional space via a separate linear layer, as we see here. Then after that, we have a gating mechanism. Gating mechanism is like to fuse the modality confidence from each module via fully connected layer and softmax to dynamically weighting the inputs to make a prioritizing for the more reliable confidence. And the other layer we use a multi-head attention mechanism, is like we added to capture across module dependencies in latent space via two head self-attention mechanism by focus on a most relative fused feature for better classification. Then we use normalization layers, which consists of a dropout to prevent overfitting. Then we use it for classifier. We use three fully connected layer that reduce the dimensional at the end to predict our four classes for the 3 drone and non-drone class. The implementation now. The implementation for acoustic drone detection. We prepare our dataset as we see in this chart. The dataset of acoustic we split it in 70 for training and 20 for validation and 10% for testing. Then the training of the CNN module, the acoustic module, we use a SGD optimizer with learning rate 0.01 that to optimize the module weight on the training set. And we use a step learning scheduler to greatly decrease the learning rate for better convergence. We enable early stop with patents of 10 epochs. Based on the validation accuracy, we add a Gaussian noise during the validation only to simulate the real world noise robustnesses. And our CNN module trained just only for 20 epoch due to the early stop. For the experiment, the evaluation of the experiment of the CNN module, we see here the accuracy, the eval accuracy we get 99.7, and with test accuracy 98.8. 82, and with the precision is near perfect results for all classes. And for recall also, that means that our CNN module is predict correctly out of the all number or of the total number of each class. By recall, we prove that. And with Afun, we have excellent phone scores confidence here for our module. And to ensure our module that learning well, we use the SNE visualizations. We see here in the training set and validation set and test set, the module successfully separate each classes, unless here there is little bit overlapping, but it is not that much. That means our CNN module is learning well. And other evaluations, more evaluation, we have confusion matrix. The confusion matrix proof there is no any misclassification, just only one missed here and one miss in the test set. That means it's a perfect result for classification, class classifications. And with per class performance, we see that for all classes, we have near perfect results. And for precision recall curve, also it's near perfect. And ROC curve prove that our module successfully in the classification of the classes. And here now for visual detection experiments. For visual detection experiment, we split our data set as 74 train and 24 val and 10 for test. As then the YOLO modules by default use augmentations like color adjustment, horizontal flips, random erasings to apply during training. That will enhance the unbalancing we have in the paired class. For training the YOLO 11S, we use SGD optimizers with learning rate 0.01 that applied optimize the module weight. We use a step learning scheduler to adjusting the learning rate dynamically during training, and we enable early stop with patterns of 10 epochs to prevent overtraining or overfitting, and would enable the automatic mixed precision mechanism, which speed up the training and reduce the GPU memory usage, as well as our YOLO 11 module trained for 100 epochs without using the early stop, and with the batch size of 16, and training times take about 4 hours on NVIDIA RTX A2012 GB RAM.
Thank you, Saad. Please keep the finish it earlier. It is only 1 minute left. Please keep the conclusion, please. Yes.
Okay, here, okay, Dr. Kim, I will try to move fast. Here for YOLO 11S, the result is the result is near perfect. Just we have for M3T drone, because it's small drone, we have the lowest results. But with main average precision, we have 91.3 for validation, and also with the evaluation of YOLO 11S module, we have perfect classification. If you see the recall confidence. But we have a lowest for the smallest drone, which is M3T. For our fusion module, before we begin training the fusion module, we need synchronized data, because our data set not synchronized at the first. We make a small data set, a small synchronized data set that's from 5-second video clip that's pairing the acoustic and visual, and pre-processing this data. Then we train our latent fusion attention module with Adam optimizer, and it's trained only for 20 epochs due to early stop. The result of our
thank you, Saad. Could you please go to the conclusion page directly?
Okay.
We have another session waiting for us. Yes.
Okay, okay, but I want to show the result here. Example for inference. We make inference on a videos to simulate a real-time detection for each drone. With in the conclusion, we we make evaluation of two acoustic module. We see that the simple CNN is outperform the complex hybrid CRNN, and we see that the YOLO 11S outperform YOLO 8S due to it is lighter and deeper architectures and better for small drone detection. And our fusion module is like fill the gaps or and the limitation of individual modalities of acoustic and visual. Like here we see comparison, we see our late fusion attention is improve the accuracy of the single modality methods. For future, okay, Doctor. For future work, just collect more higher quality data and expanding the data set and try another fusion technique like early fusion. Thank you, Dr. Kim. Sorry for.
Sorry, thank you for the very amazing presentation. Please understand that due to very time limited session, it's a very amazing research, amazing presentation. Thank you, Sanat and Safi.
Thank you, Doctor, and thank you for all. Thank you.
And finally, this conclusion our session for today. A big thank you to all our speakers and the audience for making this such a successful event. Thank you for all of us and the speakers, and we appreciate of the hostess. Let's finish our session. Thank you again.